All right, welcome back. More Physics 180. As promised, we're going to talk about potential energy and energy conservation. And the first topic we really want to cover is the thing I mentioned in the last video about work and kinetic energy, and that there are these particular special types of forces called conservative forces. Conservative forces, here are a couple of definitions. Note that these are not forces that vote Republican in U.S. elections or anything like that. Conservative has a specific meaning for us here in physics. So the work done by a conservative force on a particle is independent of the path taken. So if you look at this picture down at the bottom, I go from point 1 to point 2. I can take path A or path B, goes backwards, right? Or if I went from 1 to 2, I'll backwards along path B. It wouldn't matter. The amount of work done by a conservative force would be independent of which way I went. I could go whatever way. Or another way to say it is any conservative force is one where the work done on a particle is zero when it goes around any closed path. So if I start at point 1 and I go on path A around to point 2 and back to point 1 through any path, I get zero total amount of work done by this conservative force. So conservative forces are always defined in terms of the amount, the work they do, whether it needs to be path independent and or the closed path gives you zero. Those are mathematically, they turn out to be equivalent. That's all we need to keep track of for those. But it turns out that it's very convenient to define the work done by these conservative forces in terms of a thing called a potential energy. Energy associated with relative positions of different parts of a system. We're going to look at a couple of particular conservative forces and find potential energies associated with them. But some people say we should call this configurational energy. Maybe that ship has sailed. Potential energy is the name that's going to stick. Potential because there's the potential for this energy to turn into motion and become kinetic energy, which is going to be a big topic for us in a later video on the same topics. But we want to look at this associated change. It turns out that all potential energies are really changes in potential energy. We're talking about work being done by a conservative force. And the configuration is really from one configuration to another. So I have a beginning state and an ending state. Even though we're going to talk about potential energy of some particular things, like a gravitational potential energy of an object that we'll do here in a minute, potential energies are really always changes. For convenience sake, we'll probably dispense with always writing the change in the potential energy unless we really want to keep track of specifically a change from an initial state to a final state. But all potential energies are really differences in configurations. Where we choose the zero configuration is kind of arbitrary. They're mathematically convenient spots, but that's about it. So, gravitational potential energy. This is our first one. Remember I mentioned in the last video dropping a piece of paper from 2 meters high. I get my piece of paper here. I happen to have a piece of paper. It's not really 2 meters, but if I drop it, it just kind of falls straight down, right? But it might flop around a little bit. What if it drops like that and flutters around? Well, it turns out that the work done by gravity is independent of the path, and we can see that in here. I'm really integrating from height 0 or height h to height 0. I'm arbitrarily picking a 0 high, the ground, the top of my desk, my computer keyboard, whatever. I pick some 0 and I measure all heights above or below that. Above would be positive, below would be negative. But I calculate the work. mg is the same. The displacements, mg is always straight down, right? Straight down towards the ground or towards the center of the earth. And so even if I have a displacement that's kind of this way, only the downward component counts when I do that dot product to calculate work. And when I do that dot product, I just end up with mg times dy. I carry out the integration. M and g are constants. I take them out of the integral. I get minus h as a result. And then the potential energy is there, then mgh, this gravitational potential energy, valid for anywhere near the surface of the planet Earth, can be used again and again and again. If you want to do orbital mechanics and figure out energy to get rockets in orbit and send them to Mars and things like that, you can't assume that the gravitational potential energy is mgh, because g isn't constant between here and Mars, right? You have to do it in terms of the general gravitational force. That's another story. This is what we're going to use. We're going to do our problems here on Earth, or maybe on some other planet, but always with a nice, steady amount of gravitational acceleration, and we can shortcut gravitational potential energy as mgh. So the problem I mentioned in the end of the last video, if the paper has a mass of 4.5 grams and how much work does gravity do? Well, just minus mgh. I can calculate it. 0.088 blah 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 joules, right? Or the potential energy that it had, the gravitational potential energy it had when it was 2 meters above zero, zero being, I don't know, maybe the ground, my arbitrary zero, 2 meters higher than what I'm calling zero gravitational potential energy. I get that same amount of energy, but positive instead of negative, because it started with that and then it turns into something else, which we're going to get to here in a minute. So our first type, gravitational potential energy, really handy. We also want to look at springs. Remember the Hooke's law force, right there, the force on a spring, minus kx I hat. We'll do this in the I hat direction. Then I write ds. I'm going to calculate the work done. Oh, the dot product conveniently works out, right? And I calculate the work minus a half k x final squared minus x initial squared. Or the spring potential energy. I simplify a little bit and I just say, oh, it's spring potential energy 1/2 times the spring constant k. So let me make a note, that's the spring constant in newtons per meter, right? Times delta x squared. Delta x is the amount of stretch or compression. And you notice, since I'm squaring that, it really doesn't matter whether I stretched it out and made it more positive x or squished it down and made it more negative x. I'm squaring it so positives and negatives go away, right? And I end up with this amount of energy stored in the spring. That's a really good way to think about spring potential energy. When delta x is 0, that's if you just took the spring and just like set it on the table. You're not squishing it, you're not stretching it. It's completely relaxed. A completely relaxed spring has 0 stretch or compression, and therefore has 0 spring potential energy. If I squish it, compress it, I get positive amounts of spring potential energy. If I stretch it, I still get positive amounts because I'm squaring that amount of stretch or compression. So here's where we really get serious with energy, mechanical energy. We remember the work kinetic energy theorem from the last set of videos, right? Total net work from all the net forces equals to change in the kinetic energy, right? Well, I can divide work up into a few pieces, which I do here. I can say there could be work from external forces, work from non-conservative forces. The non-conservative forces that we really worry about in this class, friction, maybe air resistance. It's a frictional effect as well, but frictional forces, mostly surface friction for us. And work from conservative forces. But remember, work from conservative forces, that would be minus changes in potential energy. If I do a little bit of rearrangement, I can say, oh, well, change in potential, and I'll move that to the other side. I'll plug some things in, and I get this guy right here. This one that says change in kinetic energy plus change in potential energy equals work from external forces plus work from non-conservative forces, right? Or the total change in mechanical energy. Mechanical energy is just that total kinetic energies and potential energy. And remember, potential energy, we know about 2 kinds. We know about gravitational potential energy and spring potential energy. Turns out there's lots of potential energies. Chemical potential, that's not mechanical, so we won't worry about it. Atomic bonding potential energies, we're not going to worry about that. That's right. There are all sorts of potential energies, but we're just going to worry about the mechanical ones for us. It turns out that it's really convenient and relatively easy to just define a system such that there are no external forces at all. So we end up with this thing now in the double red box. Change in energy equals work from non-conservative forces. Let me put an underline, exclamation, second underline. We're going to use this a lot. It is the basic idea behind energy conservation. So changes in energy are done by non-conservative forces. Maybe external forces, but let's just define all of our systems to include all of the forces acting on the thing we care about. Then we don't have to worry about external forces. All we have to worry about is work from non-conservative forces. So this is going to be our master equation for solving most of the problems in homework number 8 about potential energy and energy conservation. This is our energy conservation formula. It really says that energy doesn't just go anywhere, it changes between things, right? Well, let's look at some quick examples here to wrap this up a little bit. I got a 5 kilogram object, You can read all these yourselves. Take a stab at answering these quick questions. It shouldn't take too long. Pause the video here, maybe spend 5 minutes and see what you can come up with, and then unpause the video and we'll look at things one by one. Okay, you of course have already figured this out because you've clearly paused the video and waited and it did all this work. Just in case, my 5 kilogram object, it has a total mechanical energy of 100 joules, and only conservative forces are at work. This means that the work from non-conservative forces is equal to 0. Therefore, any changes in energy also equal to 0, right? I'm going to do something trickier. I'm going to write this change in energy as energy final minus energy initial equal to 0, or final energy equals initial energy. This is true. So in our case, that would be 100 joules, right? But this is true so long as there are 0 non-conservative forces doing work. So I could say at any later time, if the total mechanical energy started at 100 joules and it ends, and aren't any non-conservative forces, that it'll end at 100 joules for sure. Let's take a non-conservative force. It does 10 joules of work, right? So now we say work non-conservative. Does an amount of work equal to 10 joules, but here's the thing about non-conservative friction in particular. Remember calculating work done by friction in homework 7 and some of the examples. Work done by friction was always negative. So I'm going to say work done by non-conservative force is negative 10 joules, right? Then I write this down and I say I'm going to immediately write delta E as E final minus E initial equals minus 10 joules, right? Then E final would be E initial minus 10 joules, which would be 90 joules, right? There was some lost energy. This 5 kilogram object lost some energy. I put lost in funny air quotes because it really isn't lost. We know where it went. It was work done by the non-conservative force. Turns out this turns into thermal energy, internal energy inside the objects. That's why things heat up. Rub your hands together, and you can heat your hands up, right? It's work being done by friction, and taking your mechanical kinetic energy and turning it into thermal energy, internal energy inside your hands. So the last one, if the object started with all of its energy as potential energy, it loses that 10 to those frictional effects. It ends up with all of its remaining energy in the form of kinetic energy. That means that E final equals 1/2 mv squared, right? And we'll say translational kinetic energy just to make this easy so we don't have to deal with is it rolling without slipping and blah, blah, all that stuff. We'll say it's all just translation. It's just a little point particle, right? So I could go back to that last page. I could have a 1/2 mv squared, the E final, that equals 90 joules, right? Because I had my 100, I lost 10, I ended up with 90. V equals the square root of 90 joules times 2 over 5 kilograms, right? Let's work this out and see what we get. And get my calculator here. 90 times 2, I can do that in my head. That's 180, right? Divide that by 5. That's 36. The square root of 36 is 6. Oh, that's convenient. It's as though someone contrived this to work out just right. 6 meters per second. That's how fast it's going. It's really a speed. I can't tell you what direction it's going without knowing more about its initial direction, right? I'd have to figure something. In fact, strictly speaking, it's plus or minus 6, right? When I take the square root, I'm going to take plus 6 because minuses would just be directions. I really don't know the directional information from this energy stuff. So a few quick examples of using conservation of energy. We'll see some more later. In the next video, we're going to talk about some things regarding tying those potentials back to their origin from forces and work. I'll see you then.